Hi, I'm Param Rajpura, and I'm excited to present our work, Quantifying Spatial Domain Explanations in Brain-Computer Interfaces using Earth Mover's Distance. Our code and the preprint are available on the link shared here. The recent approaches towards adopting deep learning-based motor imagery models in BCI research are driven by the advantages associated with learning complex tasks in an end-to-end fashion. However, this shift accompanies a challenge in offering interpretable and robust reasons for model outcomes. Though explainable AI approaches are utilized to justify the model performance of data-driven outcomes, the explanations from a specific model architecture are subjectively interpreted in isolation. Evaluating explanations with quantified metrics is a stepping stone towards interpretable models. To explain the model predictions, we use spatial domain explanations. In simple terms, spatial domain explanations describe the EEG channels that are most significant in determining the predicted outcomes. The spatial locations of these EEG channels signify the activity of brain regions in its vicinity. Such an explanation at the sensor level can be visually represented by the montage image shown here. To benchmark our approach, we use the PhysioNet EEG motor movement imagery dataset, one of the largest datasets on motor imagery and movement, with 64 channel EEG recordings collected from 109 participants. For the analysis, we use the EEG data from the participants while they execute or imagine left or right hand movements. Each 4-second long trial is divided into 1-second long epoch. The models are trained for binary class classification, predicting left or right hand movement or imagery. To test the explainability across different state-of-the-art techniques, we choose a Riemannian geometry-based classifier that calculates the minimum distance to the mean of covariance matrices computed from EEG data. We consider two end-to-end learning models, EEGNet and EEG Conformer. EEGNet is a convolutional neural network benchmarked across multiple BCI datasets. EEG Conformer is a transformer-like architecture with self-attention layers. All the models are trained and evaluated using 3 different data configurations. The first configuration uses all 64 EEG channels to predict the outcome. To validate the efficacy of explainable AI techniques that use data-driven feature relevance, we compare the performance of each model with the domain knowledge in neuroscience. It is known that the 21 channels positioned near the motor cortical regions, especially central, frontal central, and parietal regions, are considered important to record activity during motor movements and imagery. The accuracy metrics show that MDM classifier is the best performer, followed by EEGNet and EEG Conform. The monotonic decrease in accuracy across data configurations is also evident as we go from 64 channels to 21 channels using domain knowledge and data-driven feature relevance scores. However, these metrics do not provide a peek into what is the basis of these differences in each of the model's predictions. Understanding the fact that EEG has a low signal to noise ratio, the matrix may provide a false perception of performance or generalization. Therefore, we compare the spatial explanations by using feature relevance scores to visualize the most important channels for each model's prediction of left and right hand movement. We use distance metrics to find feature relevance scores for the MDM classifier, while for the EGNet and EG conformer, we use GradCam. The results show very few channels to be overlapping with the central, frontal central, and parietal regions considered to be important for motor activity. Therefore, it is necessary to quantify the comparison baseline on the domain knowledge in neuroscience. Considering all channels to be of equal significance, the spatial explanations from the models can be represented in the matrices as shown, and the heat maps can be compared with the baseline using Earth mover's distance. Earth mover's distance, also abbreviated as EMD and also known as Wasserstein distance, evaluates the optimal mass transportation plan, considering both values and spatial arrangements. This approach provides a robust metric for matrix dissimilarity, capturing both local and global differences. When the relevance scores of each channel are considered as weights, a similar trend is observed where MDM classifier turns out to be the closest to the baseline spatial explanation, while EGNet and EG conformer follow consecutively, separated by a relevant margin from MDM. Our study demonstrates that the performance metrics, even though seem very close for the three architectures, the explanations vary to a greater extent. The findings indicate that end-to-end data-driven approaches need to be validated in the context of BCIs, and the model interpretations should be compared against what can be expected from the literature by adding the XAI framework to the data-driven pipeline. Thank you.